Now we're going to take what we learned about the physical properties of gases and apply them in what are called named gas laws.
All right, so gases are really useful. And the most important property that we utilize of gases is the fact that they can expand and contract. That means you can change the volume of a gas very rapidly. And so one of the things that, we use it for fun things like, say, bouncy houses, right? Importantly, anything that's inflated like that, it's filled with gas. So the gas will fill the container, whatever the size is. And it'll nice inflated, it'll hold it up, give it some sort of volume. But importantly, when that gas is compressible, so if you say jump on the bouncy house, it's not firm, right? If you filled it with water, it wouldn't have any give when you go to jump on it. It would just be, firm. Whereas, the gas has that some sort of resistance, but, it kind of can still support things. We also use it in, say, air brakes on, say, like a large vehicle. You can fill up the brake really fast with a lot of air, and then that expands, and then you compress the pads against the rotors to stop the vehicle or to stop the wheel, whatever it is. We also do things, like in a pipe organ, you just let the gas expand through the opening in the pipe in order to create sound, right? So there's basically just a constant air flowing, you just let it flow, it'll constantly expand, creating sound. So we use this property as one of the biggest things when it comes to gases. And if we're going to be using gases, we want to be able to, we say we want a certain volume of gas, or we want to change the volume of a gas. We want to be able to control the physical properties of gases. So how we predict these is via using what's called gas laws. And so the whole purpose of gas laws is that they allow us to predict changes in physical properties. And what I mean by that is we know that gases, for example, can expand or contract, their volume can change. So the question is, how can I cause the volume to change in a way that I want? I want to fill up my brake. I want to inflate my bouncy house. How much gas do I need? What temperature could I change it to? How can I affect those volumes and pressures? How are these things all related? And so the thing that's unique about gases is that it doesn't matter what type of gas we're talking about. Nitrogen, oxygen, air, carbon dioxide. Their physical properties change in predictable ways. So what that means is I can make predictions about how a gas is going to change just because it's a gas. It doesn't matter what type of gas we're looking at. This is unique for gases. In solids and liquids, their physical properties will change as if you heat up the temperature, the volume, or say that something will evolve, with time, would change in response to that. But each different solid and liquid responds in its own way. Gases all consistently respond in the same way, meaning we can come up with kind of single relationships to describe how are the physical properties of any gas going to change when we affect the conditions that that gas is under. So our first example of gas law is going to be called Charles's law. So a lot of these laws initially are going to be named after people. What would happen is back up 200 years ago, scientists did some experiments to try to relate the physical properties of gases. And so whoever came up with it first got a law named after them. And so Charles, what he looked at was the relationship of temperature and volume. And you'll note that Charles's law says that temperature and volume of a gas at constant pressure are directly related. So what that means is if one of those variables, say temperature, increases, the other one will increase as well for your gas sample. So here's an example of, you just looked at, say, 1 mole. So when we say a sample of gas, what that implies is that we're looking at some sort of constant amount of gas molecules. So in this case, 1 mole, so we have 1 mole, and we're putting it under, again, constant pressure. So we're sitting it under 1 atmosphere, so it's just say a balloon exposed to the atmosphere. And then what you could do is you could look at changing the temperature of that gas and then measure how the volume of that gas responds. So here you're cooling off the balloon, you're seeing how that size changes. And the important thing we can see is that they are directly related. So as the temperature decreases, the volume would also decrease. Conversely, if the temperature were to increase, the volume would also increase. You can see we get this nice straight line indicative of a direct relationship. If we want to understand what's going on here, we can think about that this is based around the fact that gases are made of molecules. And so we know that when you have, say, a constant pressure, pressure is that sort of force. So there is we could imagine like a piston pressing onto the gas. And so that is a constant pressure, and you have, say, your gas molecules are moving around. If you turn up the temperature, say you heat those gas molecules, they will start to move faster. Higher temperatures lead to higher speeds. Those molecules are moving faster, which means that they're going to be hitting that piston more strongly. The piston has that constant pressure, same amount of force, so they're pushing it up, leading to an increase in volume. And so we can see that those molecules are just moving faster, so their volume of this overall gas sample will increase. Conversely, if you cool it off, they move more slowly, and the volume will shrink. You can't press that as hard. So the functional form of Charles' law is V1 over T1 is equal to V2 over T2. Okay, so the V and the T stand for volume and temperature. And then we'll note there are those subscripts, the 1s and the 2s. And so this is starting to get to the purpose of Charles' law, is to predict changes. And so we're going to change the volume, we're going to change the temperature. How will the other variable respond to our gas? And so the 1 and 2 subscripts correspond to the initial and final state of the gas. This is true for any of our named laws. This is Charles. We'll see some other names pop up. They are always used for changes of a gas. So if you change something about a gas, how does it respond? There is always going to be 2 descriptions of the gas, an initial and a final, beginning, end, anything like that. So let's look at an application of Charles' law. A sample of argon gas at atmospheric pressure occupies 1.3 liters. When the temperature is changed to 27 degrees Celsius, the gas occupies 4.5 liters. What was the initial temperature of the gas? All right, so the first thing we want to ask is, what do we want here? Whenever we're trying to solve a problem, we're going to start by asking, what do we want? You can see that we are looking for the initial temperature of the gas. So whenever we see that word initial, that's something we want to key in on when we're dealing with properties of gases. Because if we're asked for the initial, that means there had to have been a final. That means we had to have a change. This gas is changing. There's some sort of process affecting this gas. So when we go to then think about, we want to figure out the initial temperature, well, what other pieces of information do we have? And we can see there's a lot of other variables that are given to us. We have the 1.3 liters, 27 degrees Celsius, and 4.5 liters. We can see that all of these are temperatures and volumes that we're looking at. One thing in particular is that we were asked again about an initial temperature, and we can see that we were given a different temperature, right? We were given a different temperature of the same gas sample. That always implies we're going to be dealing with one of these named gas laws. And because we're given a bunch of temperature and volume measurements, we are likely dealing with Charles's law. Okay? If we're going to use Charles's law, one thing that we need is that the pressure has to remain constant. So thankfully, we are told that this is a process at atmospheric pressure. We are also told that it is a sample of argon gas. That implies that the number of moles is also constant. Whenever you're dealing with a sample, you're not changing how many molecules are in the sample, and that's an important part of being able to apply Charles's law. So we know that the equation for Charles's law, V1 over T1, is equal to V2 over T2. We want to then assign variables. We wanted initial temperature, so initial is going to be that 1. So we are looking for T1. That's what we're always going to be after here, is the T1 term, because that's the initial temperature. So we start with the equation for Charles's law. And we just said that what we wanted was that T1, right? That's the variable we want. So we should expect to have 3 other pieces of information, V1, V2, and the T2. We need a value for all of our other terms. So we're given the 1.3 liters, 27 degrees Celsius, and 4.5 liters. Those are going to fill all my other points. So now when I want to solve for T1, you'll notice it's in the denominator. We're going to be dealing with a lot of equations that have these ratios, these fractions. If you want a number in general when you're solving these, you're going to want to cross multiply. especially if you're trying to get a value that's in the denominator. So that way you get it out of the denominator and you're not going to deal with any sort of weird other business. It's really easy to kind of forget some of the steps when we're trying to pull a number out of there. But we can cross multiply, and then we can rearrange our equation to solve for the T1. We just divide by the V2. So when we're looking now at assigning our variables, the 1.3 liters, 27 degrees Celsius, and the 4.5 liters, we can see that when we're looking at these kind of changes, just the language is what's going to tell us whether or not it is a change or not. One of the things also is that if we're after the initial temperature, we want a T1 here, this other temperature that's given to us, the 27 degrees Celsius, has to be T2 then, right? That has to be part of T2. And so that 27 degrees Celsius is a part of the state, that's the second state. So here it is, does tell you the temperature is changed and then what the gas occupies. So you could probably figure out that this is V2 on the 4.5 liters, but we could always then predict that if it's a little more confusing, whatever the temperature, the piece of information that you're given has to be for the other state, either 1 or 2, and every other description of that kind of that gas is all going to have that same subscript. So here, because 27 is the final temperature, 4.5 liters has to be the final volume. Okay, so then that also means that 1.3 liters is my T1, which we expect in the language it says a sample just occupies that. Then the temperature is changed, so that causes the effect. So we can go ahead and plug all those in. One thing we want to note when you're using a temperature, it does need to be converted to Kelvin, just like generally when we're working through these, all of our degrees Celsius will always need to be converted to Kelvin in every single gas law application. So plug them in. You'll note that the liter and liter cancel out, and your answer is going to be in Kelvin. So when you, just like you got to put Kelvin in, it's always going to have Kelvin come out. One of the things to note, the question asked for or gave us a temperature in degrees Celsius. Usually if you're giving an answer, you want to match whatever the given units were. So we want to convert this to degrees Celsius. So we subtract 273 and get it to the 186 degrees Celsius. All right, Boyle's law then tells us that the pressure and volume of a gas sample at a constant temperature are inversely related. So as if the volume decreases, the pressure increases. So one of the things we can see is that this is different than we saw before with Charles' law. Now we're dealing with an inverse relationship. So these variables change in opposite directions. One goes up, the other goes down. So colloquially, you've experienced this. Say if you have a balloon, when you press on the balloon, right, initially it's relatively easy. That's because it's a lower pressure. And as you squish the balloon, as you decrease the volume of that balloon, it becomes more difficult to continue to compress it. That resistance to compression is pressure, right? That gas is pushing back against you and against further compression. So as you decrease that volume, as you shrink the gas down or decrease the volume, it gets harder and harder to continue to compress because the pressure has increased. So if we want to think about what that looks like, now we can see that that sort of increase in volume corresponds to a decrease in pressure, right? They go opposite directions. And conversely, if you were to decrease the volume, the pressure would decrease, right? So we can see that as you kind of go to lower pressure values, the volume is getting further and further out. So this sort of curved U is indicative, again, of inverse relationships. Those straight lines that we saw for Charles's law are indicative of a direct relationship. Our equation is going to look similar to Charles' law in that it has two variables, in this case, pressure and volume, and the subscripts. The 1 and the 2 still correspond to the two different states of the gases, right? State 1 and state 2, initial and then final. The difference here, one of the things you'll see, is that the variables are multiplied together instead of the fractions. Those fractions that we had with Charles's law corresponded to direct relationship. An inverse relationship corresponds to the multiplication that we have here. So when you multiply those variables together, it's always equal to the same amount. So you can always have different states. All right, so using it, some gas at 150 Kelvin and 2.7 bar has a volume of 3.4 liters. The gas changes to have a new pressure of 4.5 bar. If the temperature of the gas does not change, what is the new volume of the gas? We always start out by thinking about what do we want? Where do we want to end up at? And we can see that we're looking for the new volume of the gas. Okay, so again, that word new implies that this gas is undergoing a process. Initial, final, old, new. These are all words that indicate that there's some sort of change. And whenever we're dealing with a change, that's always going to signify that we're probably going to be using one of these named gas laws. And the question is just kind of to figure out which one to use. Another thing we can always key in on is we're asked for the new volume and we're given another piece of information of volume. We're given a volume of this gas in a different kind of version of the gas, before or after some sort of change. Here it's new volume, so that's going to be our old volume that we're given. So we know we have a volume. There's some other pieces of information given. The things we want to key on is that other volume, that 3.4 liters. And then whenever we're dealing with named gas laws, we're looking for things that are doubled up. Bar and bar. So we're given two pressures for the gas, right? We need two descriptions of the two states, old, new, beginning, end, whatever it is. And so we need to have that paired up. So both of the volume or both the pressures are indicative of something we'd be using. There's all pressures and volumes that are given here. So we'd be looking to apply Boyle's law. Importantly, the temperature must remain constant in Boyle's law. You'll note we're told that it's at 150 K initially. We may be tempted to try to use Charles's law, but the temperature does not change. If the temperature isn't changing, that's not what's driving the process happening. And so we don't need to worry about that. But this temperature is constant, which means we can use Boyle's law. Again, there's also no indication that the number of molecules of gas is changing. That is important. The number of moles also can't change. And generally, if that just says some gas, there's a sample of gas, that sort of language always points to that. In general, there'd be a description of how the number of molecules would have to change in order for that to be used. But Boyle's law, P1 times V1 is equal to P2 times V2. We want to go through the process of assigning variables, figuring out what we're looking for, and what all we have. And we know new volume implies that we're looking for volume 2, right? Old volume is going to be volume 1. New volume, which is what we want, is volume 2. So we better have a number for everything else. Okay, so we have our Boyle's law expression. We have all the variables we want to put in. We wanted to solve for V2, so I'm going to go ahead and rearrange my equation, just divide both sides by the P2. We know, again, that this has to be the V1. Again, it's if we read, it's like it has a volume of 3.4 liters, then we can see the gas changes. And so that happens afterwards, so that is our V1. Related to that, the gas changes to have a new pressure of 4.5 bar. That is P2. So this other variable, the 2.7 bar, has to be a part of the old or original setup. And so that P1 is going to be 2.7 bar. Similarly, we can see that 2.7 bar has a volume of 3.4 liters. Those two variables have to be linked together. They're going to be either both ones or both twos. In this case, they are both ones. So we can plug in all our numbers. We can see that bar and bar cancel out. We get a volume of liters. So the volume here, the new volume, is 2 liters. And so this sort of idea is the whole purpose of a gas law, right? We could now figure out, say you're going to have some sort of gas sample. It's going to change to have this new pressure of bar and 4.5 bar, and the new volume is going to be 2 liters. Or conversely, if you need to get to a pressure of 4.5 bars, what should you make the new volume, right? You can use this new volume that if you get this gas to 2 liters, it will now have a new pressure of 4.5 bar, which you could potentially want to use or anything like that. Another thing to note, you'll see with the pressure units here we used bar. It's a little bit, we have normally used atmospheres, and that's what we're going to see moving forward. But in the case of a named gas law like this, it doesn't matter what the pressure units are, as long as you recognize that they're pressure units and they cancel out, right? What's most important is that here and here are the same pressure unit, not what they are. It actually doesn't matter what they are. It'll work in any pressure unit, any volume unit, as long as you're consistent. So you can go from gallons of gas to gallons of gas as long as you're using those same consistent units for these named gas laws. So Boyle's law actually has some very important properties to what you are doing right now. It's how you breathe. So your breathing is all about your diaphragm. And so it's a muscle that expands and contracts. And what that does is it changes the volume of your lungs. So your lungs are flexible organ. And so when the diaphragm expands or goes down, it's actually a contraction of the muscle, we can see that the lungs expand, right? So the volume here increases. And if the volume increases, that means the pressure of the gas inside that volume, i.e. the gas inside your lungs, decreases. And so because that pressure of the gas inside your lung decreases, you're going to get a net flow of gas in because the gas outside your body has not changed in pressure, right? So that's why gas starts to flow into your body because you've expanded the volume of your lungs. Conversely, when you decrease the volume of your lungs, if you shrink it, when you decrease that volume, you know that the pressure will go up. So the pressure inside your lungs increases because the volume has decreased. All of a sudden, it's now higher than the outside pressure and air flows out of your body. And so this Boyle's law is something we use in our kind of chemical industry from, in pneumatics and moving things around. But it's also what drives how and why you can breathe. Because based on that expansion and contraction of the volume of your lungs. So we've talked about Boyle's law and Charles' law. A bunch of other people, Avogadro, Amonton, all did the same kind of process where they looked at two variables, they held two other variables constant and figured out what the relationship was. So one of the things you'll note in all of these, it's the 1 and 2 state. So these named gas laws are all about relating changes in gases. There are always two constants. The other two variables are constant. We have 4 physical properties of gases. 2 are constant, 2 change. And then the only question is it an inverse relationship, which means they multiply together, or is it a direct relationship, in which case you have the fractions. So those relationships, we can parse out all of these different relationships between the different physical properties of gases. Participation 629, question 2. A constant pressure of oxygen gas, O2, is heated from 120 degrees Celsius to 212 degrees Celsius. The final volume is 20.3 liters. What was the initial volume? This is the second question on participation 629, due Monday, June 29th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, a constant pressure of oxygen gas is heated from 120 degrees Celsius to 212 degrees Celsius. The final volume is 20.3 liters. What was the initial volume? Okay, second question for participation 629. See you in the next video.